Picture a box of air, split down the middle by a thin wall, and set into that wall one tiny door. A shutter so light it takes no effort to slide open or shut. Now put a little gatekeeper beside it, small enough to see the individual molecules come and go. All day they rush around, some fast, some slow, a jostling crowd with no plan. Our gatekeeper just watches. Every so often it slides the weightless shutter. When a fast molecule comes flying from the right, it opens the door and lets that one pass to the left. When a slow one drifts up from the left, it lets that one slip back to the right. It never pushes anything, never spends a drop of energy. It only watches and opens a door that costs nothing. And slowly, with no work and no fuel, one side of the box grows warm while the other grows cold, all by itself. That quiet little sorting, if it were real, would be enough to break the most ironclad law in physics.
And it gives me a shiver every time, because for well over 100 years, nobody could say exactly why it fails. That little gatekeeper is one of the most famous creatures in physics, and it is not a cartoon. You can write down precisely what it does, and when you do, it really does seem to make heat flow the wrong way for free. The reason it cannot actually work turns out to be one of the deepest ideas in all of modern science, and one most people have never heard stated plainly. Here it is. Hold it loosely until we've earned it. Information is physical.
Okay, that sentence means nothing to me yet, and I refuse to nod along to it. But I'll be honest, the setup already bugs me, in the good way. My first reaction is that you can't do that. You just described the hot side getting hotter and the cold side colder on their own, and I'm pretty sure I spent a whole month of thermodynamics learning that exactly this does not happen.
Say more. What's the rule you think it's breaking?
Wait, this is just entropy and the second law, right? Heat flows from hot to cold, never the other way on its own. Entropy never decreases. That's the one law they told us has no exceptions, ever. So my instinct is just to say no and go home. But the way you said it, it sounds like the no is harder than I think.
The no is much harder than you think, and that is the whole story. Getting to a satisfying no took physics from 1867 all the way to the 1980s, and then, astonishingly, into laboratories in our own century. So let's not go home. Let's start exactly where you started, with the law you already own, and then watch this little gatekeeper threaten to tear it up and see what it actually costs to save it. Wait, this is just the second law, right? So plant your feet. Tell me the second law, the way it lives in your head.
A few ways, and I think they're the same thing wearing different clothes. 1. Heat flows from hot to cold, never spontaneously the other way. 2. Entropy, the messiness, the disorder, of an isolated system never decreases. It stays the same or goes up. And 3, the one from statistical mechanics that I actually find kind of beautiful, entropy counts arrangements. Boltzmann's formula, entropy equals K times the logarithm of W, where W is the number of microscopic ways you could arrange the pieces and still get the same big picture state. High entropy just means there are astronomically more ways to be like this, so that's where things drift.
That is exactly right, and I want to dwell on that third version, the counting one, because it's the key to the whole night. Entropy isn't some fluid that leaks out of hot things, it's a count. A gas spread evenly through a box is high entropy because there are unfathomably many arrangements of molecules that all look spread evenly. A gas crammed into one corner is low entropy because there are so few ways to do that. So when we say entropy tends to increase, we just mean systems drift from rare, special arrangements toward common, generic ones, because there are astronomically more of the common ones. That's the engine under the hood.
Right, and that's why the second law always felt less like a law and more like a near certainty. It's not forbidden for all the air in the room to rush into one corner. It's just spectacularly unlikely, because almost every arrangement has it spread out.
You have just put your finger on something it took the greatest physicists of the 1800s a while to swallow. The second law is not an absolute iron commandment like conservation of energy. It is statistical. It holds because the numbers are so enormous that unlikely becomes never for any box of gas you'll ever meet. And the man who saw that most sharply is the man who invented our little gatekeeper to make the point. James Clerk Maxwell, the same Maxwell whose equations you learned in electricity and magnetism.
The Maxwell. Okay, so this is his creature. When?
In a letter. December of 1867, Maxwell writing to his friend, the physicist Peter Guthrie Tait, saying, I love this, that he wants to pick a hole in the second law. And he describes exactly the gatekeeper you opened with, a finite being, he called it, who can see individual molecules and work a little frictionless shutter in a partition, sorting fast from slow. He put it in print a few years later in his textbook on heat, around 1871. And notice his purpose. He wasn't claiming a perpetual motion machine. He was making a philosophical point with teeth. The second law is only true because we are big and clumsy and can't track single molecules. A being who could would not be bound by it.
So Maxwell invented it as a thought experiment to show the law is statistical, not to actually break physics. Where does demon come from? Because that's a loaded word for a devout Victorian physicist to be throwing around.
Good instinct, and you're right. Maxwell never used it. He only ever wrote finite being. The word demon was hung on the creature by another giant, William Thomson, Lord Kelvin, in the journal Nature around 1874. And here's the thing everyone gets wrong. Kelvin didn't mean an evil spirit. He meant it in the old Greek sense, a demon, a tireless little background helper that does a humble job over and over. Maxwell's demon is not malevolent, it's just diligent. It sorts.
A diligent little sorting spirit. That's almost worse, honestly, because it sounds so reasonable. So let me make sure I feel the threat properly before you rescue me from it. The demon sorts fast from slow. Fast molecules on the left, so the left heats up, slow on the right, so the right cools down. It built a temperature difference out of a uniform box, and a temperature difference is exactly what you feed a heat engine to get useful work. So the demon manufactured order and free energy out of nothing but watching.
Out of nothing but watching and opening a costless door. And I want you to sit in the discomfort of that, because if you wave it away too fast, you'll miss the whole lesson. Sorting the molecules lowered the entropy of the gas. You took a generic, spread-out jumble and turned it into a rare, sorted arrangement, hot here and cold there, and by the story so far, you paid nothing for it. If that stands, the second law is dead, and a huge amount of physics with it. So this is a real threat. Taking it seriously is the price of admission. The demon has to know.
All right, I'm taking it seriously, and it's making me itchy. So where's the crack? Because there has to be one. My whole thermodynamics course can't be a lie.
It isn't, and the crack is hiding in a word I've used a dozen times and you've let slide. Watching. The demon has to watch. Before it can decide whether to open the door for a given molecule, it has to find out, is this one fast or slow? It has to measure. And then, this is the part that took a century to appreciate, it has to remember the answer, at least for a moment, long enough to act on it. The demon doesn't just sort, the demon knows.
Okay, but knowing sounds free, it's just noticing. Looking at a molecule and going, yep, fast one, why would that cost anything? A thought doesn't weigh anything.
And there's the trap, so let me spring it gently. When you say the demon knows a molecule is fast, Where does that knowledge live? To be used, to trigger the shutter, the answer has to be written down somewhere physical. Some little switch has to flip. The position of something, the orientation of a tiny magnet, a bit of charge here rather than there. Information is never free-floating. It always rides on a physical thing that is in one state rather than another. That's the first quiet crack. To know, the demon must write, and writing happens in matter.
So you're telling me the demon has a notebook, a physical notebook, where it jots down fast or slow for every molecule it checks.
A notebook is exactly the right picture. And let me flag it as a picture, an analogy, because in a minute it's going to have a hard, sharp limit that matters enormously. But yes, hold the notebook. Every measurement writes one entry. And now ask the question a bright student always asks, the one that kills the demon.
The notebook fills up. It's a physical object, it has finite pages, and the demon runs forever. Eventually there's no room left to write the next molecule down.
There it is. That's the thread that unravels the whole thing. The notebook fills up. So the demon's notebook fills. And if it wants to keep sorting, molecule after molecule, forever, it has only one option: make room. It has to erase old entries to free up pages, reset the memory back to blank so it can be written on again. And that innocent little act, erasing, forgetting, wiping the page clean, is where the entire bill comes due. That's the catch. And the person who found it was not a philosopher and not an astronomer. He was an engineer at a computer company.
A computer company? Why is IBM in my thermodynamic story?
Because by the middle of the 20th century, the people who most needed the true, unavoidable energy cost of handling information were the people building machines that handle information for a living. And in 1961, a physicist at IBM named Rolf Landauer asked a question nobody had nailed down. Is there a fundamental, unbeatable minimum energy cost to a computing step? And he found something startling. Most computing steps can, in principle, be done for free. No minimum at all. But one specific kind of operation cannot. Erasing information, wiping a bit, forcing it to a known blank state, must unavoidably dump heat into the surroundings. There's a flaw beneath it no cleverness can dig under.
Hold on, I need the why, not just the that. Why would erasing specifically cost anything when writing and reading are apparently free? That feels backwards. Erasing feels like the easy one. You're just clearing the page.
It feels backwards until you look at it through Boltzmann's counting, and then it's almost obvious. This is my favorite turn in the whole subject. Take one bit of memory. Before you erase it, it could be in either of two states. Call them 0 or 1. You don't know which. It's carrying a real answer, so it's genuinely one of two possibilities. Now you erase it. What does erase mean? It means, whatever you were, now you're 0. Two possible starting states, one guaranteed ending state. You have squeezed two possibilities down into one.
Oh, and number of possibilities is exactly the thing entropy counts. So squeezing 2 down to 1 is literally lowering the entropy of the memory. You made it more certain, more ordered, fewer arrangements. And the second law does not let you lower entropy for free.
You just derived Landauer's principle in your own words, and I could not be prouder. Erasing a bit lowers the entropy of the memory. The second law says that drop has to be paid for. It has to be pushed out somewhere as an increase in entropy of the surroundings, and the currency for that is heat. So erasing one bit forces you to dump a minimum amount of heat into the environment. And Landauer nailed the exact minimum. It's a specific little quantity, and I'm going to spell it the way physicists say it out loud. kT log 2.
Break that into pieces for me. Slowly.
The K is Boltzmann's constant. The very same K in your entropy equals K log W formula, the bridge between counting arrangements and measuring energy. The T is the temperature of the surroundings on the absolute scale, and log 2 is just the logarithm of the number 2, because you collapsed exactly two possibilities into one. Put them together, erase one bit, and you must dissipate at least K times T times the log of 2 as heat. That, at least, is the soul of it. You can waste more. You can never spend less.
Give me a feel for the size of it. Is this a lot of heat or a little?
Fantastically little. At room temperature, around 300 Kelvin, kT log 2 comes out to about 3 zeptajoules. And a zeptajoule is a joule divided by a billion, then by a billion again, then by another 1,000. A joule is roughly the effort of lifting an apple off a table. This is that, shattered into a billion thousand pieces, and you take 3. It's almost nothing. But, and this is the entire point, it is not nothing. It is strictly, provably, unavoidably greater than 0. Forgetting costs heat. Not much, but never 0.
Can I test the picture because I want to make sure I know where the cost really lives? You said writing and reading can be free, but erasing can't. What's the actual difference? They all feel like doing something to the bit.
The cleanest question you could ask, and the answer is a single phrase. Logical irreversibility. Watch. If I copy a bit, or flipping it, I can always run the movie backwards. From the output, I can recover the input, because no information was thrown away. Those operations are reversible, and reversible operations have no forced cost. But erasing is different in kind. After I erase, the bit reads 0, and I have no way to tell whether it used to be a 0 or a 1. That information is gone. Many possible pasts, one present. You cannot run it backwards. That destruction of which state it was is what forces the heat. So the careful statement is not, computing must dissipate heat. It's sharper. Only the logically irreversible steps, the ones that genuinely throw information away, carry the unavoidable price.
That's a real distinction, not a hand wave. And now I have to hold you to the notebook analogy, because you warned me it had a limit. A real paper notebook does cost something to erase. Friction, a worn-out eraser, smudges. Isn't Landauer's cost just that, the ordinary messiness of a real device?
No, and this is exactly the limit I promised to flag, the most important sentence in the analogy. The cost of erasing a paper page, friction, ink, eraser crumbs, depends entirely on your technology, and in principle, a better eraser drives it down toward 0. Landauer's kT log 2 is not like that. It doesn't depend on how you build the memory. It doesn't care whether your bit is a magnet, a charge, a molecule, a bead. It's set by one thing only, the temperature, and no improvement in engineering, ever, by anyone, can beat it. It's not a practical cost. It's a flaw written into thermodynamics itself. That's what makes it profound instead of merely annoying. Landauer had a slogan for the whole realization, the sentence I asked you to hold at the very start. Information is physical. The book's balance.
Okay, so bring it home to the demon, because I can feel the pieces, but I haven't watched them click. The demon sorts, which lowers entropy and looks like free work. But it has to measure and remember, which fills a notebook, which eventually has to be erased, and erasing costs at least kT log 2 per bit. So where do the books land?
They land exactly even, and it's gorgeous. Let me give you the cleanest version, which strips the demon down to its skeleton. One molecule, one bit. It's a machine dreamed up by a Hungarian physicist named Szilard in 1929, the Szilard engine. And let me flag as your guide that it's an idealization, a one-molecule gas, a frictionless piston, none of it buildable in a machine shop. The point isn't the hardware, it's that the exchange rate becomes exact and countable.
One molecule of gas, a box with a single atom bouncing around in it. Go.
A box with one molecule, touching a warm bath at temperature T. Step 1. The demon looks and learns which half the molecule is in. Left or right, 1 bit, 0 or 1. Step 2. Knowing which side is empty, it slides a piston in from there, costing nothing because there's nothing to push against. Step 3. The lone molecule keeps bouncing off the piston, and those kicks push it back. The gas expands against it, and the demon harvests that push as work, drawing heat from the bath to power it. Do the accounting on that single isothermal expansion, and the work extracted comes out to exactly kT log 2. 1 bit in, kT log 2 of work out.
Wait, that's the same quantity. The work I pull out of 1 bit of knowledge, kT log 2, is the exact same size as the heat I have to dump to erase 1 bit of memory. That can't be a coincidence.
It is not a coincidence. It is the universe keeping its books. Every bit of knowledge the demon acquires lets it extract at most kT log 2 of work. And to acquire the next bit, it eventually has to erase the last one, which costs at least kT log 2 of heat. Gain and cost, the same size, staring at each other across the ledger. Net profit over a full cycle, 0, or worse, if the demon is the least bit inefficient. The demon never got anything for free. The second law was never actually in danger. We had simply forgotten to write the information down as a real physical entry in the accounts.
So the resolution isn't the demon is impossible, it's that the demon is possible, and it really does lower the entropy of the gas, but its own memory picks up exactly enough entropy to balance the ledger, and the second law survives once you count that memory as part of the physics.
That is precisely it, and you said it better than most textbooks. Now I owe you some honesty about how this was won, because the history isn't as tidy as the punchline. For decades, the standard story located the cost in the wrong place. A physicist named Léon Brillouin argued in the 1950s that the demon pays when it measures, that to see a molecule, it must bounce at least one particle of light off it, and that generates the entropy. The cost is in the looking. That view held for a long time.
And you're using the past tense very deliberately, so I'm guessing it was wrong.
It was shown not to be the fundamental cost by another IBM physicist, Charles Bennett, in 1982. Bennett showed that measurement can, at least in principle, be done reversibly, with no forced minimum at all. So Brillouin had put the bill in the wrong place. The truly unavoidable step, the one you can never make free, is erasing the memory to reset the demon for the next round. That's the Landauer cost, and it exactly cancels the demon's winnings. This Landauer and Bennett picture, the cost lives in erasure, is the standard resolution you'll find in textbooks today.
I hear a but coming, and I want it, because you've been honest all season about the difference between settled and still argued.
Then here's the honest edge, and I won't paper over it. Exactly where in the demon's cycle the irreducible cost has to sit, the measurement step or the erasure step, is still genuinely argued among specialists. There are recent papers, even in the last year or two, revisiting whether the true price is really in the erasing or back in the measuring. That bookkeeping is live. But, and this is the part not in dispute by anyone, when you count the total thermodynamic cost of the demon's information handling, wherever you decide it sits, the books balance and the second law is saved. The demon is defeated. The argument is only over which line of the receipt to underline.
That's a distinction I can hold. The rescue is certain, the exact accounting is still being polished, and now I think I finally understand your opening sentence, but I want to say it back carefully, because it's the kind of phrase that could go badly mystical if I'm sloppy. Information is physical means to store a bit, move a bit, erase a bit, you have to move real energy and real entropy around in the physical world. Information has a price tag set by physics. That's it. It does not mean information is some glowing substance, or that thoughts weigh something, or…
Stop right there, because you're about to say the thing I most want to fence off, so let me do it with you. It does not mean any of that. Information is physical is a precise, modest, and shocking claim about the thermodynamic cost of manipulating information. It is not a claim that the universe is secretly a computer, and it is emphatically not a statement about consciousness, or free will, or the soul. The demon's knowing is a magnet pointed up or down, not a mind having an experience. The precision is the honesty. Keep the claim exactly as narrow as it really is, and it stays true and stays astonishing. Let it swell 1 inch past that, and it turns into mysticism. So, information has a physical price, full stop, and the whole of it is plenty. Catching the demon in the act.
So this is all a beautiful, century-long argument. Maxwell to Szilard to Landauer to Bennett, all of it on paper. Please tell me somebody eventually caught it in a lab. Because KT log 2 is a fantastically tiny amount of heat, and you spent that whole first conversation this season telling me a prediction isn't real until someone measures it.
Somebody did, and the fact that it took 50 years after Landauer wrote it down tells you how hard it is. The quantity is so absurdly small, 3 zeptojoules, that to see it you need a single microscopic object you can watch in exquisite detail while it forgets 1 bit, with almost no other heat sloshing around to drown it out. That experiment finally arrived in 2012. A team in Lyon, France, Antoine Beroux and colleagues, in the group of Sergio Ciliberto, built a memory out of a single microscopic bead in water, held by focused laser light in a little double trap, 2 tiny valleys left and right. The bead in the left valley is a 0, in the right valley a 1. 1 bead, 1 bit.
And to erase it, you force the bead into one chosen valley, no matter which one it started in. Squeezing 2 possibilities into one, the exact thing you said costs heat.
Exactly that. They gently reshape the light to sweep the bead always into, say, the right valley, wiping out which side it began on. And because they could watch its every jiggle, they could measure the heat dumped into the water during that erasure. And here's the result that gave the field goosebumps. As they did the erasure more and more slowly and gently, squeezing out every bit of avoidable waste, the heat dropped, and then flattened out. It saturated. It came down to a floor and refused to go lower. And that floor sat right at KT log 2, exactly where Landauer said it would 50 years earlier. The bound is real. It was measured.
That gives me chills, honestly. A number reasoned out from pure thermodynamics in 1961, sitting untouched for half a century because nobody could build a delicate enough experiment, and then a single bead in water confirms it. Has anyone pushed the other direction, actually run a demon forward and pulled work out of pure information?
They have, and this one might be even more wonderful. And it came a little earlier, 2010, a team in Tokyo, Shoichi Toyabe and Masaki Sano and colleagues. Picture a tiny particle in water, jostled by thermal noise, on a kind of spiral staircase. A landscape tilted so downhill is where it wants to slide. Thermal kicks are random, so every so often, by pure chance, a kick knocks the particle a step uphill, against the tilt. The instant that happens, the experimenters, playing the demon, see it and quickly raise a barrier behind it so it can't slide down.
So they never push it, they just watch, and when luck carries it up a step, they lock in the gain. Ratchet by ratchet, on nothing but noticing which way the noise happened to jump. That's the demon, exactly. No work done on the particle, only information about where it is.
No work done on it directly. They lifted that particle up the staircase, against the force, using nothing but knowledge of its position. They converted information into free energy, a real physical Szilard engine running on a bench in Tokyo. Which brings me to the fence I have to build right now, before your imagination runs off with it.
Let me guess. No, this is not perpetual motion. No free lunch.
No free lunch, and I need you to say it with me and mean it. It's deeply tempting to hear, you can extract work from information and slide into free energy forever. You cannot. Every joule those experiments squeezed out was at least matched by the cost of acquiring and ultimately erasing that information. Resetting the apparatus, running the feedback, wiping the record. Landauer's KT log 2 is a floor on what it costs, not a jackpot you collect. The books always balance or come out behind. There is no perpetual motion machine hiding anywhere in this story, and anyone who tells you there is selling something. A floor tied to the temperature is exactly that, a floor, not a payout. The honest horizon.
You promised at the start this was the season finale, and you've been ending every one of these by walking me to the edge and showing me what nobody knows yet. So do it. Where's the frontier from here?
3 places, and for each I'll tell you what's solid and what's open, same as always. The first quietly rewrites a law you thought was carved in stone. Go back to something you said an hour ago in passing. The second law isn't an absolute commandment, it's a near certainty about huge numbers. For a whole box of gas, that near certainty is so overwhelming it might as well be a law. But for one bead, one molecule, one tiny jittering thing kicked around by heat, the numbers aren't huge anymore. And down there, something strange is allowed.
Strange how? Are you about to tell me the second law can actually fail for one little particle? Because you've been very strict all season about not saying reckless things.
And I'm going to stay strict, so listen to exactly how I phrase this. For a single small system, the entropy can, now and then, by pure chance, momentarily go the wrong way. A little dip against the second law, for an instant, for one trajectory. That is real and it happens. What is not true, and I won't let it be said loosely, is that the second law fails. The law holds on average and with overwhelming probability. The tiny backward dips are outweighed by more frequent forward steps, so the average always obeys it. And in the late 1990s, 2 physicists made this shockingly precise. Christopher Jarzynski, in 1997, found an exact equation, not an inequality, an equality, connecting the work you do, dragging a small system between 2 states to an underlying energy difference, true even when you yank it hard and fast, far from equilibrium. And Gavin Crooks, around 1999, found a companion relation for the precise ratio of how often the process runs forward versus backward.
So instead of the old, entropy increases, greater than or equal to, a one-sided inequality, these give you an actual equals sign for the little fluctuating world. The second law stops being a wall and becomes a precise statement about odds.
That's the spirit of it. These are the fluctuation theorems, the rigorous bridge between the demon's single-particle world and the bulk thermodynamics in your textbook. And I'll be honest about the limit of what I'm giving you. The real machinery is a graduate subject, and I'm handing you only the headline. The headline is enough. For tiny systems, the second law is reborn as an exact law of probabilities, not a vague one-way arrow. Those very theorems, by the way, are what the Tokyo team used to prove their engine obeyed the rules.
I love that. Second place?
The second is where this stops being about beads and lasers and starts being about you. Living things. A cell is full of little molecular machines that look an awful lot like demons. Motors that walk along fibers, pumps that push ions the wrong way across a membrane, and above all the machinery that copies your DNA with almost unbelievable accuracy. And accuracy is the tell. Getting a copy right means rejecting errors, sorting right from wrong, which is exactly the demon's move. Back in 1974, a physicist named John Hopfield showed how cells pay for it. A scheme called kinetic proofreading, where the cell deliberately burns extra energy to double-check its work and throw away mistakes. You spend free energy to buy accuracy. You pay to reject entropy.
So life is running tiny Maxwell's demons all over my body right now, paying the thermodynamic bill exactly the way you'd predict. That's a wild thought.
It is, and here's where I hold the analogy line hardest, because it's the most seductive one tonight. That cells pay energy to buy accuracy, kinetic proofreading, is solid, established, beautiful physics. But a cell is a Maxwell's demon is a research framing, an illuminating analogy people are actively investigating right now. Not a proven identity, not a theorem. The machinery of life clearly plays the demon's game and pays the demon's kind of price. Whether it's right to say it simply is a demon is a live, unsettled question. Take it as a doorway, not a conclusion.
Doorway, not conclusion. And the third?
The third is the plainest, and you'll feel it in your own life. Every computer, every phone, every data center burning a city's worth of power, all of it is bound, at the very bottom, by this. There's a fundamental thermodynamic flaw to the energy cost of computation, and we established tonight what sets it. Right now, our machines run 1,000 to 1 billion times above that flaw. The open engineering frontier, one of the great ones of this century, is how far down toward the Landauer limit we can push real, useful computing before the physics we talked about stops us cold. Nobody knows where the practical wall is, but we know exactly where the ultimate one is. And that's a rare and beautiful thing to be able to say about any frontier. The hidden character.
Can I take a second? Because this is the last one, and I don't want to just rush off to a problem set. I want to actually notice what just happened over this whole season.
Take all the time you want. This is the right moment for it.
When we started, the very first conversation, the black holes, you said something that annoyed me, that the frontier is one honest step past the homework I did this week. I thought that was a nice line to make undergrads feel included, but it kept being literally true. An accelerating charge, straight out of my E&M homework, became listening to space-time. The wave function, from my first quantum course, became 1,000,000 atoms marching in one step and became qubits. Symmetry, which I thought was just a trick for doing integrals faster, became a law written into the very shape of matter. Every single time, we started somewhere in my textbook and walked one honest step, and there was the edge of what anybody knows.
You've just named the architecture of the whole season better than I could. Go on. I think you're about to find the thing I was hoping you'd find.
And there was someone else there the whole time. I didn't notice until tonight. Information kept showing up. It was hiding in the arrow of time. Why the movie only plays one way. It was in that strange conversation about what falls into a black hole and whether anything is truly lost. It was in the qubit, obviously. And tonight it finally walked into the middle of the room and took a bow, in the driest corner of all of physics, the second law, the rule about steam engines and heat. And that rule turned out to be quietly guarding the deepest secret of the bunch.
And that secret is the sentence you refused to nod along to an hour ago, and now you've earned it. So let me say it back as the real ending of the whole season. Information is not some bookkeeping we lay on top of physics. It is not separate from the world. Knowing, forgetting, measuring, computing, these are physical acts with a real, unavoidable, now measured price, set by nothing more than the temperature of the room. The driest law in your textbook turned out to be a law about information all along. That's what the demon was trying to tell us for 150 years. It just took us that long to listen.
And the honest part, because you'd never let me leave on a clean bow, is that it isn't finished. We measured the floor, but we don't know exactly which step pays the bill. We can build a demon on a bench, but we can't yet say for certain that the machinery in my own cells is one. And there's a whole ocean of room between the computers we build and the ultimate limit, and nobody knows how close we can get.
All true, all open, and all yours if you want them. That's the thing I most want you to carry out the door. Every frontier we visited this season, the ripples in space-time, the cold atoms, the topological matter, the demon at the door. Everyone was, not long ago, thought to be permanently out of reach. And in every case, people not much older than you, standing about where you're standing, took one honest step past the textbook, then another, and reached it. That was never a slogan. The frontier really is one honest step past the page in front of you. You've just spent 12 conversations proving it to yourself.
One honest step past the page. That's what I'm taking with me. I came into this season half suspecting the real frontier was a walled garden for geniuses, some far-off country I'd only read about. And instead you kept handing me the gate and showing me it wasn't locked. So, thank you for not blowing smoke, for not dumbing it down, and for trusting me to hold the difference between what we've proved and what we only hope.
That difference is the whole craft. Hold it in two hands your entire career, and you'll never be fooled, and you'll never stop being amazed. Now go. There's a little demon at a little door in every hard problem, whispering that you can get something for nothing. You know how to answer it now. Count the information. The books always balance.
The books always balance. That's a good place to end a season. Until next time, keep taking the honest step. The edge is closer than they told you, and it's been waiting for you the whole time.